Hello guys, welcome back to my channel Algorithm Avenue. In our previous video, we have discussed about an important topic called regularization. Now, in this video, we'll be discussing about another important topic called activation functions. Okay, these activation functions are referred to as very important topic with respect to deep learning. Okay, now let's discuss the basic definition of activation functions. Okay, in artificial neural networks, each function forms a weighted sum of its inputs and passes resulting scalar value through a function referred to as activation function or transfer function. Okay, this activation function is also referred as transfer function. Okay, now let's decode this definition with an example. Okay, now let's say this is my artificial neural network. Okay, now I'm considering this neuron. Okay, now I'm considering this neuron. In first part of the definition, what it is saying, in artificial neural networks each neuron forms a weighted sum. Okay, now how actually this weighted sum is calculated is, this weighted sum is calculated by multiplying inputs with weights and adding bias. Okay, by multiplying inputs with weights and finally adding bias. Okay, this weighted sum is represented by z. Z is equal to x1 w1 plus x2 w2 plus b1. Okay, in this way we represent weighted sum. Okay, now we completed our first part of the definition. Now in the second part of the definition, what it is saying, the resultant scalar value. Okay, this is the scalar value. This scalar value must be passed through a function. Okay, the scalar value must be passed through a function. Okay, okay, this scalar value I'm passing through a function and representing my output as a naught. Okay, I'm passing this weighted sum through an activation function. Okay, through a function which is referred to as activation function. Okay, this function is referred to as activation function. I'm passing this weighted sum through a function, activation function, and my final output is represented by a naught. Okay, in this way we have successfully decoded our definition. Now let's see the importance of this activation functions. Okay, this activation functions determine which neuron to be activated and which neuron to be deactivated. Okay, activation functions determine which neuron to be activated and which neuron to be deactivated if it's activated. Okay, if the neuron is activated, how much percent should it be activated? Okay, this is the basic funda of activation function. Okay, there is another advantage of using this activation function, that is to draw non-linear decision boundaries. Okay, the first use of activation function is to determine which neuron to be activated or deactivated. The second advantage of using the activation function is to draw non-linear, okay, sorry, non-linear decision boundaries. Okay, now let's see what is meant by non-linear decision boundary and what is meant by linear decision boundary. Okay, let's say this is my data set. Okay, this is my data set and I have two classes in it. Okay, this x is my class and this dot is my another class. Now without using activation function, my decision boundary is on straight line. Okay, now you see that for a non-linear data I'm drawing a linear decision boundary. Okay, by doing this our model will not be able to predict well. Okay, our model is not able to classify well. Okay, now by using this activation function, our decision boundary will turn out to be this one. Okay, this is the decision boundary after using the activation function, and this is the decision boundary without the activation function. Okay, this is with respect to classification. Now with respect to regression, okay, with respect to regression, let's say mm, let's say this is our data. Now without using activation function, This will be my regression line. Okay, this is my regression line. Now when you compare this point to this regression line, you see that there is so much loss. Okay, it is not able to predict well. Now by using activation function, our decision boundary will turn out to be this. Okay, this is a decision sorry, this is a regression line. Okay, this is the regression line before using activation function, and this is the regression line after using the activation function. Okay, this is the basic use of activation function. Okay, the first use of using the activation function is it determines the activity and deactivity of the neuron. And the second basic advantages of using the activation function is to classify nonlinear data. Okay, to do nonlinear regression or nonlinear classification. Okay, these are the two advantages of using the activation function. Now in the next part of the video, we'll be taking a data set and we'll be applying linear activation function. Okay, linear activation function means no activation function. Okay, linear activation function means no activation function, and we'll be seeing the model results.
Now let us take a non-linear dataset and apply a model which doesn't have any activation function in the hidden layers. Okay, now I am importing my necessary libraries and I'm taking the make circles dataset, and this is my dataset which contains two classes. One is blue and another is red. Okay, this is a non-linear dataset, and I am splitting my data into training and testing. 20% of my data is going to testing and 80% of my data is going to training, and then I am converting from numpy to tensors, and this is my model which doesn't contain any activation function. You can see that it is linear activation function, means it is not having any activation function in the hidden layers. The Z is passed as it is to the next neuron. Okay, now I am naming this model as no activation model, and the loss function is BC with Logit's loss, and optimizer is Adam optimizer with learning rate 0.01 and accuracy function, and from here to here is my training loop, and this entire is my testing loop, and I am printing my model results for every 100 epochs. Okay, at the 100th epoch I got around 49.25% training accuracy and 48% test accuracy. You can see that the model predictions are not at all accurate. Okay, now let's observe the decision boundary. Okay, now when you observe the decision boundary, you can see that it is a linear straight line which is trying to classify this non-linear data. Okay, and linear straight line is trying to classify non-linear data. Okay, so that is why we are not able to get accurate predictions. Okay, this is the basic disadvantage of not using activation function.
In my previous section of the video, when I taken a non-linear dataset for classification and used a linear activation function. Okay, linear activation function means no activation function. Okay, when I applied no activation function, my decision boundary was linear. Okay, now in this section of the video, we'll be seeing why basically the decision boundary was linear on that non-linear dataset, and we'll be also understand the use of activation function. Okay, now this is my artificial neural network, and I have represented my weights with W1, W2, W3, W4, W5, W6, and my bias with B1, B2, B3. Okay, now what we'll be doing is we'll draw corresponding. Okay, we'll try to determine corresponding weighted sum and activation function outputs for each neuron. Okay, now I'm doing corresponding to this neuron. Okay, this neuron weighted sum, I'm representing it as Z1. Okay, Z1 is equal to X1 W1 plus X2 W2 plus B1. Okay, now I need to pass this Z1, okay, this weighted sum value through an activation function. Okay, now I'm assuming my activation function as linear activation function, means no activation function. Okay, now when I pass this through an linear activation function, my output will be, let's say, A1. Okay, when I pass this weighted sum through a linear activation function, my output is A1. Okay, A1 is equal to Z1. Okay, now the weighted sum, okay, when the weighted sum is passed through linear activation function, it is same as, okay, it is same as the weighted sum. Okay, means no activation function is being applied on that weighted sum. Okay, now let me determine with respect to my second neuron. Z2 is equal to x1 w3 plus x2 w4 plus b2. Okay, this is my second weighted sum value, and I'll be applying the same step over here. That is g of z2, it is denoted by a2, and this is also equal to z2. Okay, it is same as this z2 value. Okay, now I'm calculating corresponding to this neuron. Okay, yeah, I'm representing this as z3. Z3 is equal to a1. Okay, a1 w5 plus a2 w6 plus b3. Okay, a1 w5. Okay, the output of this neuron is represented as a1. You can call it as a1 or z1, and the output of this neuron is represented as a2, or you can also call it as z2, as you are using a linear activation function, and I am adding bias. Okay, now what I will be doing is I'll be just replacing this a1 with this entire scalar value. Okay, now a1 is equal to x1 w1 plus x2 w2 plus b1. Okay, this is multiplied with w5. Now what I'll be doing is I'll be similarly replacing a2 with this scalar value. Okay, I'm replacing this a2 with this scalar value. Okay, a2 is equal to x1 w3 plus x2 w4 plus b2. Okay, this is multiplied with w6 and added with bias b3. Okay, now I'm doing the multiplication. Okay, I'm multiplying w5 inside and w6 inside. Okay, now x1 w1 w5 plus, sorry, plus x2 w2 w5 plus b1 w5 plus I'm multiplying w6 inside x1 w3 w6 plus x2 w1 w6 plus b2 w6 plus added with b3. Okay, now in the next step what I will be doing is I'll be just rearranging the terms. Okay, all this bias, okay, all this bias terms I'll be placing in one side, and all this weight and input terms I'll be placing in one side. Okay, I'll be grouping them based on this scenario. x1 w1 w5 plus x2 w2 w5 plus x1 w3 w6 plus x2 w1 w6 plus b1 w5 plus b2 w6 plus b3. Right, now observe clearly, this entire terms are the combination of inputs multiplied with weights. Right, this entire four terms, okay, this entire four terms are the combination of input multiplied with weights. Okay, now what I will be doing is I'll be replacing these four terms with value called xw dash. Okay, I'm replacing this entire four terms for simplicity with xw dash. Okay, and I'll be replacing this entire three terms with b dash. Okay, now after replacing with this values, my final, okay, my final z3 value becomes xw dash plus b dash. Okay, this is my final output. Okay, final output through this neuron. Okay, now when you keenly observe the relationship between the output and input, okay, you observe the relationship between the output and input. The input is in the form of ax plus b. Okay, this ax plus b is the equation of a line. Okay, this ax plus b is the equation of a line. Right, means the relationship between the input and output is linear relationship. Okay, the relationship between the inputs and outputs is linear relationship. So that is why the linear decision boundary, okay, the linear decision boundary is being drawn in the previous part of the video. Okay, now instead of using linear activation function, if you could have used another non-linear activation function, the relationship between the input and output could be non-linear, right? Okay, if you use instead of linear activation function some any other non-linear activation function, the relationship between the input and output could be non-linear. So when the relationship is non-linear, non-linear decision boundaries are drawn, right? So this is the basic advantage of using the activation functions. Okay, now in the next part of the video we'll be discussing the basic qualities of a good activation function. Till now we have seen the benefits of using an activation function in an artificial neural network. Right, now in this section of the video we'll be discussing the qualities of a good activation function. Okay, to use an activation function in an artificial neural network, it must possess some qualities, okay, so that it can perform well. So now we'll be discussing what are the qualities that the activation function must possess for the better classification or regression. Right, now the first quality is non-linearity. Okay, generally in real world the data sets are non-linear. Okay, this is my non-linear data set. Now, when you apply linear activation function to it, the decision boundary will be a straight line. Okay, linear straight line. Now, when you observe this linear straight line, it is unable to classify. Okay, it is unable to classify my two classes. Okay, my predictions are very bad over here. Okay, now to work on this non-linear data, we need to introduce some non-linearity to it. So, when I introduce some non-linear activation function, my decision boundary will turn out in this way. Okay, this decision boundary is able to classify my two classes really well. Okay, so this is the basic quality. This is the basic quality of an activation function. Okay, the activation function must be non-linear to capture the non-linearity in the data. Okay, my second quality is differentiable. Okay, generally in back propagation we apply gradient descent algorithm. Okay, in gradient descent algorithm we do differentiation. Okay, now to differentiate the basic qualities, the graph must be continuous. Means an activation function, okay, when you use an activation function you need to make sure that the graph of the activation function is linear, oh sorry, is continuous. Okay, sorry, is continuous. The graph of the activation function is continuous so that it is differentiable at any point, and when it is differentiable you can use gradient descent algorithm well effectively. Okay, this is the second quality of a good activation function. Okay, the third quality is computationally inexpensive. Okay, now when we activation function, let's say this is my activation function. Now when you do differentiation to it, it is simple. Okay, it is 2x. It is really simple, right? Now let's say this is my activation function. Now when you try to differentiate this value, it is very much difficult. Okay, generally in gradient descent what we do differentiation, right? So differentiating this term is very much easy, but differentiating this term is really harder. So when differentiating this term is really harder, the training time will become very slow. Okay, the training time will increase. Okay, so when training time increases, the training will become slow and the results will not be much effective. Okay, so the activation function we use must be inexpensive. Okay, computationally inexpensive. This is the third basic quality of a good activation function. Okay, the fourth quality is zero center. Okay, now let's say this is my hidden layer. Okay, now this is my hidden layer and this is the activation function output of this each hidden unit. Okay, now when I calculate the mean of this each numerical value, the mean must be 0. Okay, the mean must be 0. Now this hidden unit output plus this hidden unit output plus this hidden unit output plus this hidden unit output, and sum divided by this 4 must be is equal to 0. Okay, the activation function must be 0 centered. Okay, now I'll be discussing about the zero centered quality in the next section of the video, while I'll be explaining about the Sigmoid activation function. Okay, the fifth quality is non-saturating. Okay, this non-saturating is nothing but, let's say I'm using Sigmoid activation function. Okay, the sigmoid activation function crushes the output from any numerical value to 0 to 1, right? Any numerical, let's say it may be 1000 or 2000, any numerical value, but it brings down in between 0 to 1. Now when the output is between 0 to 1, what actually happens is, uh, in back propagation, okay, generally in back propagation you apply a chain rule, right? Okay, do I had by do z into something, you do some chain rule, right? Now when you apply and saturating, okay, some saturating activation function, it brings the output from 0 to 1. Okay, now when it brings the output from 0 to 1, each each differentiation value will be a very small numerical value. Okay, each differentiation value in the back propagation chain will be a very much smaller numerical value. Now when you multiply each of the smaller numerical value, the resultant value will be very much smaller, right? So this is the problem of vanishing gradient. Now when vanishing gradient problem is faced, generally the training stops and weights and bias updation will be stopped entirely, means the entire training will be stopped. Okay, so the activation function we use must be non-saturating. Okay, these are the 5 basic qualities of a good activation function. Okay, generally when you use an activation function in an artificial neural network, make sure that at least it satisfies 50% of these qualities. Okay, now in the next section of the video we'll be discussing each of the activation function in detail. In this section of the video, we'll be discussing about the various activation functions that are most widely used in the deep learning. Okay, among them, our first activation function is sigmoid activation function. We have seen the purpose of using the sigmoid activation function in various binary classification tasks. Okay, at the output layer, we used to use an sigmoid activation function for the prediction of binary classification, either 0 or 1. Okay, now we'll go through the sigmoid activation function in detail. Okay, this is a basic graph of sigmoid activation function. It's an S-shaped continuous graph. Okay, the minimum value of sigmoid activation function is 0, and the maximum value, okay, the maximum value of the sigmoid activation function is 1. Okay, now let's see how basically this sigmoid activation function actually works. Okay, now let's take an example. Let's say this is a neuron. Okay, now when we divide this neuron into two halves, in the first half we calculate the weighted sum, that is the z. Okay, we calculate the weighted sum, that is z. Okay, now this z must pass through an activation function. Okay, the z must pass through an activation function. Let's say the activation function is sigmoid activation function. Now let's see what happens to this z when it passes through the sigmoid activation function. Okay, this is the basic formula of sigmoid activation function, that is 1 by 1 plus e to the power of minus z. Okay, now this calculated weighted sum value passes through the sigmoid activation function, that is this value. Okay, this z value is replaced by this weighted sum value. Okay, let's say the weighted sum is 10. Now here we calculate 1 by 1 plus e to the power of minus 10. Okay, this is how sigmoid activation function actually works. Okay, now let us see how sigmoid activation function works as a binary classifier. Okay, now let's say we have a threshold value that is 0.5. Okay, basically at the basic level we set the threshold value as 0.5, but at the higher and advanced levels we'll be deciding this threshold value based on the data and model used. Okay, now at the basic level we are taking the threshold value of the sigmoid activation function as 0.5. Okay, now we have calculated and weighted some value, and we have passed this weighted sum value through our sigmoid activation function, and we got an output as 0.6. Okay, now this 0.6 is compared to 0.5. Okay, as 0.6 is greater than 0.5, the prediction of the activation sigmoid activation function will be 1. Okay, now let's say the activation function output is 0.4. Okay, now this 0.4 is compared with 0.5. Okay, as 0.4 is less than 0.5, the prediction will be 0. Okay, you might have a doubt that if the probability, okay, if the probability is 0.5, now what will be the output of the sigmoid activation function? Okay, now this 0.5 is compared with this 0.5, as they are equal. When in the case of equal, okay, in the case of equality, the prediction will be 1. Okay, in the case of equality, the prediction will always be 1. Okay, now the when the probability is greater than or equal to the threshold value, the prediction is 1. In else if it is less, the prediction is 0. Sorry for the inconvenience. This is how sigmoid activation function actually works. Okay, now let us see the advantages and disadvantages of sigmoid activation function. The first advantage of sigmoid activation function is it can be used as binary classifier. Okay, as the outputs of the sigmoid activation function are either 0 or 1, so it can be used as a binary classifier. Okay, in binary classifier we have two classes, either dog or cat, either 0 or 1, either yes or no. So in the similar way, the sigmoid activation function also has two classes, either 0 or 1. Okay, so this is how the sigmoid activation function can be used as binary classifier. Okay, the second advantage is non-linear activation function. Okay, the sigmoid activation function is non-linear activation function. Okay, in the real world scenarios, we'll be getting non-linear data sets. So to find non-linear patterns in the data sets, we need non-linear activation function. Okay, thus the sigmoid activation function is non-linear activation function. Okay, you can see that the graph of the sigmoid activation function is non-linear. Okay, it is non-linear, it's shaped continuous curve. Okay, you cannot see any straight line over here, right? You can see some non-linear curve. Okay, so by this we can say that it is a non-linear activation function. Okay, the third advantage is it is differentiable. Okay, you can see that it is continuous. Okay, it is continuous. At the time of gradient descent, we calculate the partial differentiation. Okay, we do the partial differentiation. So while calculating the partial differentiation, the graph must be differentiable at any point. Okay, at any point. Okay, the entire graph must be, the entire curve must be differentiable at any point. So you can see that the sigmoid activation curve is continuous and it is differentiable at any point. So it is the third advantage of sigmoid activation function. The the disadvantage of sigmoid activation function is, first is saturating. Okay, the sigmoid activation function is saturating. Okay, now what is meaning of this saturation is, generally, the sigmoid activation function scales down any numerical value to 0 to 1. Okay, let's say it may be 10,000, 20,000, 30,000, any numerical value in between 0 to 1. Okay, any numerical value is scaled down to 0 to 1. Okay, either it may be 0 or it may be 1, either the numerical value may be in between 0 to 1. Okay, now in this case, what actually happens is, when you use a sigmoid activation function in the hidden layers, okay, in the hidden layers, the output of the each hidden layer will be between 0 to 1. Okay, let's say it may be 0.02, another neuron output may be 0.002. Okay, in this case, when we multiply, okay, when we multiply this gradient values, okay, this gradient terms in the back propagation, we face the smaller gradient update. Okay, we face the small weight update. So this is the vanishing gradient problem. Okay, this is vanishing gradient problem. So by using sigmoid activation function in the hidden layers, we face vanishing gradient problem. So the sigmoid activation function cannot be used in the hidden layers, only it is preferable to use in the output layer. Okay, this is the problem of saturating. Okay, The second problem of sigmoid activation function is non-zero center. Okay, I have already told you in the previous section. I'll be explaining what actually is meant by non-zero centered in the time of explanation of sigmoid activation function. Okay, now let's see what actually is non-zero centered. Okay, so to understand non-zero centered, first let's understand what is meant by zero centered. Let's say this is our hidden layer and these are our hidden units. Now each hidden unit will have an output, right? Each hidden unit will have an activation function output. Now when I calculate the mean of this four numerical values, okay, when I calculate the aggregate of this four numerical values, if they are equal to zero, okay, if they are equal to zero, it is meant by zero center. Okay, it is meant by zero center. Okay, if they are not equal to zero, it is meant by non-zero center. Okay, now what is the advantages of being this zero centered is the training will be faster. Okay, when the mean, okay, when it is zero centered, okay, when it is zero centered, the training will be faster. Okay, when it is non-zero centered, the training will be slow. Okay, so while you use a sigmoid activation function in the inner hidden layers, they become non-zero centered, means training becomes slow. Okay, now let's understand with an example. Let's say this is our neural network and this is our hidden layer and this is our output layer. Okay, the activation function output of this neuron is A21 and the activation function output of this neuron is A22, and the weights are W21 and W22 and bias is B31. Okay, now this is the expansion. Okay, this is the gradient expansion, and okay, this is the gradient expansion of each of the derivatives. Okay, now when you keenly observe, okay, this is the gradient expansion with respect to this and this is the gradient expansion with respect to this. Now when you keenly observe, these two derivative values, okay, these two terms are equal. Okay, in this calculation, okay, in this gradient calculation, these two derivatives are equal. Okay, the only variation that we are getting is this derivative value. Okay, now z31 is equal to, z31 is the output of this node. Okay, z31 is the output of this node, and when we calculate z31, z31 comes out to be a21 w21 plus a22 w22 plus b31, right? Now when I differentiate it with respect to w21, these two terms will be 0 and I'll be left out with this term, and this comes out to be a21. Okay, similarly while I differentiate with respect to w22, this comes out to be 0 0 and this comes out to be a22. Okay, now observe keenly, this is a21. Okay, this entire term is a21 and this entire term is a22. Okay, now when I use the sigmoid activation function in the inner hidden layers, the output of this a21, okay, a21 is positive. Okay, why it is positive? The sigmoid activation function is the sigmoid activation function output is always between 0 to 1, right? Okay, the sigmoid activation function output is always between 0 to 1. Okay, means it is always positive. Okay, so a21 is always positive and a22 is also always positive. Sorry, a22 is also positive. Okay, now both these values are entirely dependent on this term. Okay, both these values are dependent on this term. Okay, as this is positive, this is positive. If this is negative, okay, if this term is negative, positive into negative will be negative. Okay, this term will become negative. Similarly, as this term is equal to this term, it will be negative, positive, and this entire term will become negative. Okay, now let's say, okay, now let's say we are calculating the mean. Now we are calculating the mean for this two nodes. Okay, we are calculating the mean for this two nodes. Now as this value is negative and this value is negative, let's say the negative value is -2. Okay, this entire term value is -2 and this entire term value is -2. Sorry, -1. This entire term value is -1. Now when I calculate the mean for both this, it will be -1.5, right? It is not being 0 but it's being -1.5. Now similarly, let's say this is positive and this is positive, this entire term will be positive and this entire term will be positive. Now when you calculate the mean for both the positive numbers, it will not be 0 but always will be not equal to 0. Okay, this is the meaning of non-centered. Okay, as sigmoid activation function is non-zero centered, so it is not used in the hidden layers. Okay, as you use the when you use the sigmoid activation function in the hidden layers, the training process will become slow. Okay, this is the second disadvantage of sigmoid activation function. And the third disadvantage of sigmoid activation function is it is computationally expensive. Why it is computationally expensive? Because finding the derivative value for this term is difficult, so it is computationally expensive. Okay, these are the basic advantages and disadvantages of sigmoid activation function. Okay, sigmoid activation function should always be used at the output layer but is not preferable to use in the hidden layers. Okay, now let us quickly discuss about the rest of the two activation functions in detail. Among them, the second activation function is Tanh activation function. Okay, Tanh activation function is also used for binary classification, same as the sigmoid activation function, but the only difference comes is this negative value. Okay, this negative part is only difference between the sigmoid activation function and Tanh activation function. Okay, now when the values are less than 0, okay, when the values are less than 0, in the case of sigmoid activation function, we have put the predicted value as 0, but in case of Tanh activation function, the prediction will be -1. Okay, the prediction will be -1 for the negative values. For the positive values, the prediction will be +1. Okay, basically the sigmoid activation function, sorry, Tanh activation function will be always ranging from -1 to +1. Okay, Tanh activation function will be always ranging from -1 to +1. Okay, whereas in sigmoid activation function the range is from 0 to 1, but in case of Tanh activation function the range is from -1 to +1. Okay, any numerical value is scaled down between -1 and +1. Okay, now let's say we have gotten weighted sum value. Now the weighted sum value, when you apply sigmoid activation function in the neuron, it's substituted in this formula. Okay, e power z minus e power minus z divided by e power z plus e power minus z. Okay, the weighted sum value is substituted in the formula, and this formula output, okay, this activation function output is from -1 to +1. Okay, this is a basic working of Tanh activation function. Okay, now let us see some basic advantages and disadvantages of Tanh activation function. The first advantages of Tanh activation function is it is non-linear. You can see by the graph it is non-linear. Okay, it is non-linear graph. Okay, it is a non-linear continuous graph, so it is able to find the non-linear patterns in the data. Okay, this is the basic advantage of Tanh activation function. The second advantage of Tanh activation function is it is differentiable. Okay, as it is a continuous graph, it is differentiable at any point. Okay, as it is continuous graph, it is differentiable at any point in the graph. Okay, this is the second advantage of Tanh activation function. The third advantage of Tanh activation function is it is zero centered. Okay, why it is zero centered? In sigmoid activation function we only have the values ranging from 0 to +1. Okay, 0 to +1 means we have only positive values, as Tanh activation function scales down numerical values in between -1 to +1 will be having both positive as well as negative values. Okay, positive as well as negative values. So by having the positive and negative values, we can make the output of the neurons as hidden units as 0 center. Okay, this is the advantage of Tanh activation function. Now let us see the basic disadvantages of using the Tanh activation function. Okay, it is saturating. Okay, this Tanh activation function, similar to the sigmoid activation function, cannot be used in the hidden layers. Tanh activation function and sigmoid activation function are not preferable to use in the hidden layers, as they scale down numerical values in between some range. So while you apply this range in the hidden layers, we face the problem of vanishing gradient. Okay, we face the problem of vanishing gradient, so they are not preferable to use in the hidden layers. They are only preferable to use at the output layers. Okay, the second disadvantage is it is computationally expensive. By the formula you can see that while you try to derive this value, it becomes very complicated derivative value. Okay, each time in the gradient descent, okay, each time in the gradient descent calculation, to find the derivative of this expression, it will be much more expensive. Okay, it will be much more expensive. So that is why Tanh activation function is not preferred much over sigmoid activation function. Okay, sigmoid activation function is most widely used, but Tanh activation function is not most widely used because of this problem. Okay, it is computationally expensive, so due to this the training becomes slow. Okay, the third activation function is ReLU activation function. Okay, this is the activation function that is used in the hidden layers. Okay, rest of the two activation functions are used in the output layer, but ReLU activation function is used in the hidden layers. Okay, why it is used in the hidden layers is, okay, basically it doesn't scale down. Okay, it doesn't scale down any numerical value. Okay, the ReLU activation function doesn't scale down, okay, any numerical value. It doesn't scale down in between some range. Okay, this Tanh activation function and Sigmoid activation function, as they scale down between some numerical value, we face the vanishing gradient problem. So as the ReLU activation function doesn't scale down between some numerical value, we don't face vanishing gradient problem, so we can use comfortably in the hidden layers. Okay, now let us understand ReLU activation function. Okay, the graph of the ReLU activation function is this way. Okay, it is a non-linear graph. Okay, it is not linear graph, but it is non-linear graph. Okay, the values that are less than 0 are 0. Okay, let's say -1, -2, -3, any negative values. When you pass through the ReLU activation function, they become 0, but all the positive values become positive. Okay, this stay as positive. Okay, now let's say you have passed +4. Okay, +4 through ReLU activation function. Now what this does is max of, okay, max of 0 comma 4. Okay, what is the maximum of 0 comma 4? That is 4. Okay, when the z value is equal to 4, the ReLU activation function output is also 4. Okay, the positive values stay positive, but the negative values are scaled down to 0. Okay, the negative values are scaled down to 0. Okay, this is how ReLU activation function works. Okay, the z value, okay, the z value will be z after applying the activation function, but when the z value is negative, they become 0 after applying the ReLU activation function. Okay, now let us discuss the basic advantages and disadvantages of ReLU activation function. The first advantage of ReLU activation function is it is non-linear. You can clearly see that it's a non-linear graph. Okay, it is not in some linear straight line, but it is a non-linear graph. Okay, the second advantage is it is not saturating. Okay, it is not saturating for positive region. Okay, when the values are positive, it is not scaling down, but only when the values are negative. Okay, when values are negative, it is scaling down to 0. Okay, but when it is positive, it is not scaling down, so it is preferred to use in the hidden layers. Okay, the ReLU activation function is preferred to use in the hidden layers. The third advantage is it is computationally inexpensive. The rest of the two activation functions, the formula to calculate the, sorry, to the formula to calculate the derivative. Okay, the derivative value of this formulas are difficult, but in case of ReLU activation function, the derivative values is very much simple. Okay, so it is computationally inexpensive and most preferred to use in the hidden layers, as training becomes faster by using the ReLU activation function. Okay, this is the third advantage of ReLU activation function. Now comes the disadvantage. The first disadvantage, it is not differentiable. Okay, when you keenly observe the graph, you see that at this point, okay, at this point the ReLU activation function graph is not differentiable, but at the rest of the graph it is differentiable. Okay, only at the point 0, only at the point 0 the ReLU activation function is not differentiable, but the rest of the graph the ReLU activation function is differentiable. Okay, this is the first disadvantage of using the ReLU activation function. The second disadvantage is it is same as non-zero center. Okay, you see that the positive values are staying positive and the negative values are scaled down to 0. Okay, so you'll be having only positive sign over here. Okay, when you have only a positive sign, it becomes non-zero center. Okay, but by using some techniques we can make it as zero center. Okay, this is a basic ReLU activation function. Now in the next section of the video we'll be taking a dataset and we'll be applying Sigmoid and ReLU activation functions to it.
I'm using the same dataset, that is make circles non-linear dataset. The only change I am making over here is I'm adding ReLU activation function. Okay, I'm changing my model such that it is able to capture non-linear features in my non-linear dataset. Okay, you can see that I'm adding ReLU activation function for each of the hidden layer, and I named this model as activation model. Okay, this is my entire model, and my loss function is BC with logits loss, and optimizer is Adam optimizer with learning rate 0.01, and this is my training loop, and this is my testing loop, and I'm printing my model results for every 10 epochs. Okay, you can see that my training accuracy is around 85% and my test accuracy is around 85%. Okay, just 0.5% difference between my training accuracy and test accuracy. Okay, now let's see my decision boundary. You can see that I have got a non-linear decision boundary, but in the previous case you can see that the decision boundary was just a straight line, but here you can see that the decision boundary was non-linear. Okay, due to this we can say that the activation functions helps in capturing the non-linear patterns in a non-linear dataset. Okay, non-linear patterns in the non-linear dataset. This is the advantage of using the activation functions in the hidden layers and output layers. Okay, hope you like this video. If you like the video, please consider like, sharing and subscribing my video. Thank you.